Hello everyone. In this video, we will see piecewise linear transformation using MATLAB for image enhancement, and this will improve the visibility in both dark and bright areas by dividing intensity levels into the linear segments. Piecewise linear transformation, it divides the gray level range into the segments, and then it will apply different linear mappings to each segment. And these are useful when certain intensity ranges need enhancement while others should remain unchanged. So the common types include contrast stretching, gray level slicing, and intensity level thresholding. Here the image is divided into three linear intensity regions. First is low intensities, that will be below R1. This R1 and R2 are the control points, that is the input control points. For low intensities, the image will be linearly stretched to enhance the dark regions. Mid intensities will be between R1 and R2, and here the contrast is increased. High intensities will be above R2, where the image will be compressed in order to reduce the brightness. And here the result is better visibility and enhanced contrast in selected regions. Now here you can see the image will be of low contrast, that is it will lack uh, visual clarity. Here we'll apply the transformation where we'll set the control points and adjust the pixel intensities linearly. Once we are done with this, we get the high contrast image, which is it is enhanced and the appearance is visual. Okay, that is it will be having an enhanced visual appearance or visual appeal. So this is another figure which depicts the same thing, that is here we are having a low contrast image then which lacks in which lacks in visual clarity. After that, what we'll do is we define the control points. The control points are R1, S1, R2, S2. So here the two control points which we are using are a combination of R1S1 and R2S2, which will divide the intensity range into three parts. And each part is linearly mapped using a formula in order to either stretch, compress, or preserve the contrast in those regions. And after that, the pixel intensities are adjusted linearly. That is, we apply the transformation and then we'll get a high contrast image which will be having an enhanced visual appeal or appearance here. This is the flow of the program where we'll read an input image, we'll convert it to grayscale if it is a color image, then we'll convert to double, that is we'll change the image data type to double for processing. After that, we'll define the control points. So once the control points are defined, these control points, these will adjust the contrast dynamically across the intensity ranges. After that, we'll initialize the output image. That is, we'll create a blank image here in order to store the transformed image. Once the blank image is created, after that we'll apply the transformation. That is, we'll apply the piecewise linear transformation to each pixel. Then we will display the results. That is, here we'll show the original and the transformed images side by side. Now we'll see the program. As usual, we'll start our program with the three basic commands, that is CLC, clear, and close all. CLC clears the command window so that the output looks tidy. Then the clear, it will remove all the variables from the memory in order to avoid any accidental reuse of the variables. And close all, it will close the figure windows if it is open. And these three commands keep your MATLAB session fresh before the script runs. Next is we'll read and convert the image. So here imread, img is equal to imread. I have copied a path for the image here. You can change this according to your image. Here imread, it loads the image file into the img variable. And for color image, the img is m into n into 3, that it will be having 3 channels. and if it is a color image, then we'll convert it to gray level by using the command RGB to gray. And here we'll use the variable img underscore gray for the gray level image, grayscale image. Now once that is done, we'll use the im to double uh, of img underscore gray, which converts the image to double precision and scales the pixel values to the range 0 to 1. After that, this block will be, that is after this block, okay, after this block, here the image will be a 2D double array with values 0 to 1. And in in these two lines, we are defining the piecewise mapping points. We are taking r1 is equal to 0.3, r2 is equal to 0.7, s1 is equal to 0.1, and s2 is equal to 0.9. You can take any values, but the condition is r1 must be less than r2 and s1 must be less than s2. Here r1 and r2 are the input intensity breakpoints, and these must be in the range 0 to 1. And S1 and S2 are the output values which will correspond to R1 and R2 correspondingly respectively, and they also should be in the range 0 to 1. Okay, condition is R1 must be less than R2, S1 must be less than S2, and all these must be in the range 0 to 1. Now next we'll create logical mask for the three regions. So here we are using low is equal to img less than R1. Here this low is true for pixels with intensity less than R1. Then mid is equal to img greater than or equal to R1 and img less than R2. Here we are taking it as greater than or equal to R1, which means that R1 is included. And here we are taking img less than R2, which means that R2 is excluded. And this is true. Mid is true for pixels between R1 and R2. Next we have high, which is true for pixels greater than or equal to R2. Okay, now next we will apply the formulas to these masks. So here we'll pre-allocate the output. In the next step from this, we'll pre-allocate the output and we'll apply the piecewise formulas. So pre-allocation is done in this command, out is equal to zeros size of img. Here this command, it makes an output image the same as the size of the image, that is here img, which we have taken, which we have converted to double, and these are initialized with zeros. Okay, these are initialized with zeros, so it is a blank array. And here this is called as a pre-allocation, and this pre-allocation is efficient. Now next what we'll do is we'll apply the formulas for low pixel. For low pixel, here out of low, okay, for low pixel we are using this formula, that is S1 by R1 into img of low. Similarly for mid, we are using S2 minus S1 divided by R2 minus R1 into img of mid minus R1 plus S1. Okay, here this one. Next is for high pixels, that is R greater than or equal to R2, R greater than R2, greater than or equal to R2. Here this maps, here we are using the formula 1 minus S2 divided by 1 minus R2 into img of high minus R2 plus S2. Okay, so here these will map R to R2 and S to S2. Similarly, R is equal to 1 and S is equal to 1, keeping the top end consistent. So because we apply each formula only where its mask is true, this MATLAB will fills entire group of pixel in one vectorized operation. Next we will display the images, that is we'll use the figure window. Okay, here we'll use the figure window. We are using the figure command where it will open a new figure window. Then we'll subplot 1 comma 2 comma 1, that is we are using one row 2 columns, and the first cell is activated here for the original gray image, that is for the gray image which we are taking as the original image. Then second is subplot 1 comma 2 comma 2. Here the second cell will be activated in order to show the piecewise linear output image. So this is the output here. This is the original image and this is the piecewise linear output. Okay. So here you are remapping input intensities R to new intensities, yes, using piecewise linear curve. Okay. So here you can see the changes in the image. Here the contrast is low. Okay, that is this is somewhat the contrast is low, and here it is the contrast is increased here. Somewhat it is black. Okay, here it is black. You can see the difference in the color. Similarly, this image. Now we will see the MATLAB program for this. Already I have copied the program here. Just will run it. See. This is how you get the piecewise linear output. Hope you have enjoyed the video. Thank you.